Okay, so welcome everybody to this special festive colloquium where we're trying basically to have a bit of fun with physics and the season. Um, I should remind you, I found this beautiful image online. I should remind you that even although this is remote, the UBC Vancouver campus is on the traditional, ancestral, and unceded territory of the Musqueam people. So I encourage you to find out more about the Musqueam and the land on which UBC is located. I wanted just to say a couple of introductory remarks just to set the lighthearted tone, hopefully. So we hear a lot about thermodynamics, which is an important branch of physics. There's two things you should know about thermodynamics. So one of them is that it's the study of heat, and the second one is that it's an anagram of me and my ostrich, which I always thought when I first learned about thermodynamics, the instructor just wrote me and my ostrich on the board and waited for the class to figure out what on earth he'd written that on the board for. So that's the one thing I always remember about thermodynamics. But today we're not going to talk about thermodynamics. We're going to talk about the study of cold rather than heat. So that maybe that's cryodynamics, and a special prize for anybody who finds a good anagram for cryodynamics. So we're going to talk about cold as a topic in physics. And sometimes people say that cold doesn't really exist, it's just the absence of heat. But lots of people know that cold really exists and wouldn't believe you if you told them that it doesn't exist. So here's an example from a popular festive movie. There are also people who can manipulate cold because they understand how it works. So there are also examples of that from movies. And I'm not saying that the people speaking to you today are superheroes, but they are young physics researchers who understand enough about physics, and they're interested in things that happen in winter that they're going to try and explain some of them to you today. So it's going to go in this order. So we're going to start off talking about snowshoeing with Ryley. Daniel's going to tell us about avalanches. Raelyn's going to talk about ice formation. Simon is going to talk about speed skating. Ryan's going to do snowboarding, and we're going to end with Megan talking about curling. Let me just say a couple of other things, which is because there's a bunch of presentations, feel free to post questions in the chat because the speakers who are just finished speaking can easily answer them for you. We'll do a question period, but we'll leave the whole thing till the end. But feel free to post questions in the chat in the meantime. And then also at the end, we might do a sort of festive gallery screenshot so you have time to go get your reindeer antlers or post an interesting background or something, and we'll take screenshots of everybody. So with that, let me hand it over to Ryley, who can start.
Hello, everybody. I'm going to talk to you today about how to stay above the snow. Has this ever happened to you? If so, I can help. So, first thing to talk about when trying to stay above the snow is buoyancy. So buoyancy is the force that keeps people afloat in liquid substances like water. Usually, what happens when you immerse a snowshoer in a pool of water is that they will displace a certain amount of volume of water equal to the weight of their body. And in doing so, they float. Now, with snow, the situation is a little bit different. When you stand on a pile of snow, you will sink into the snow, and beneath you, the snow will become compressed. And the mechanism that prevents you from falling all the way down through the snow to the bottom, to the ground below, is the density of the snow beneath you will change up into the point where it is strong enough to hold your weight. So the question is, how far will you sink into the snow? In order to get an idea of how to answer this question, we can look at the equation of state of snow, which is shown here. So this shows you how what the resulting density of snow will be for a given applied pressure. Now, when you are standing on snow, you are applying a pressure to the snow. And as you sink through the snow, you will carve out a volume which is proportional to the area, the surface area of your shoes, times the depth at which you fall. So the change in density is proportional to the surface area and the height, the amount by which you will fall into the snow. So now there are two things that can change h, the amount by which you fall. The first thing is, for a fixed pressure, the initial density of snow can be different. So if you imagine standing on very, very dense snow, which is already almost dense enough to hold your weight, you're not going to fall very far. You don't need to change the density by very much. Therefore, you don't need to change your height by very much. Or on the opposite end of things, if the snow is very light and fluffy, not dense at all, you are going to have to change the density by quite a bit and therefore fall through the snow by quite a lot. The other thing that you have control over is the pressure that you apply to the snow. Now, the pressure is exactly equal to your weight divided by the area. So if you can decrease your mass, you will decrease the pressure, or if you can increase your area, you will decrease the pressure and thus sink through the snow a bit less. Now, let's look at the first thing. What determines the density of the snow? So it turns out that the density of snow is roughly proportional to the temperature at which, the ambient temperature of the air when the snow fell. So if it's warmer when the snow falls, it will be denser. And then if it's colder when the snow falls, it will be less dense. However, of course, the snow is a bit more complicated than just that. I mean, for example, you can see that the largest snowflakes happen to fall at a temperature of minus 15 degrees Celsius. And on top of that, when it's windy, large snow crystals can bump into each other and shatter into smaller snow crystals. Or when it's windy, maybe the snow crystals will bump into each other and fuse to form bigger crystals. It could go either way. Snow is a very complicated phenomena, and there is still a lot of unknowns with snow. But generally speaking, warmer weather, the snow will be more dense and you'll have an easier time staying on top of it. So now let's look at the second quantity. All right, and so, you know, here's a chart of various snow densities at different times during the life cycle of snow. So for example, when snow is falling, its density tends to be about 100 kilograms per cubic meter. If you let the snow sit there for a while, it will just naturally increase in density as it compresses due to its own weight. And then once it starts to heat up, once the spring rolls around and the sun starts to have an effect on the snow, this will increase the snow's density as well. So over time, snow will become more dense if you just let it sit there. So now let's think about surface area. Humans, of course, have figured out how to change their surface area for thousands of years. In the modern era, we have things like snowshoes, skis, and snowboards. So here are typical surface areas of equipment that you might be walking on snow with. As you can see, boots have a surface area that is about 10 times less than snowshoes, which themselves have slightly less surface areas compared to skis and snowboards. But in principle, you just need to increase your surface area with some of these items shown here, and you'll have an easier time floating on snow. In addition to that, you always have control over your mass. You can carry less weight with you when you walk out onto the snow. However, you need to make sure that you bring all of your safety gear. All right, thanks. Good luck and stay safe.
Thanks, Ryley. Can we move on to the next presentation? And meanwhile, please feel free to post questions in the chat to Ryley. Okay, Daniel, it's all yours.
Right, so Ryley just told us a little bit about snow. And so, of course, when you're snowshoeing, you need to be cautious when you're going out into the backcountry of avalanches. Avalanches are, of course, my favorite type of collective motion, although usually not when I am snowshoeing. So first of all, if you've never seen an avalanche, this is what it might look like if you are in the backcountry. So this falls on the leeward slope, the wind-loaded slope. and he's on something about 30 degrees or so, and that's usually when you're going to start seeing avalanches more typically. And he's about to trigger a slab avalanche here. So you can see there was a fracture line, and then everything below that sort of liquefied as the slope gave way. And this is actually not a tremendously large avalanche, but it is, you know, quite significant. If somebody had been down there, they might have been in some trouble. And I mentioned the size of avalanches. Of course, avalanches can happen at very different scales. Many of us have probably seen Class 1 avalanches while out skiing. If you found, you know, a nice chute with some powder that nobody's gone down, you've probably triggered some yourself. And those are no issue. But of course, you know, these avalanches can go all the way up into the scale where they're wiping out towns or small villages and things like this. And of course, you know, you should get a sense that this scale should be, you know, in some way logarithmic, maybe like the Richter scale is for earthquakes. And let's actually make that a little bit more exact. So what I'm going to show you here, this data on the right is basically the size of avalanches observed at a French ski resort over about 3 years. It includes both man-made and natural avalanches. And what you're counting here on the y-axis is basically how many avalanches of a certain size and above did you see. So what you should get a sense of is that bigger avalanches are rarer, but they still happen, and that the size of these avalanches can vary by many orders of magnitude. And I'm going to be showing a couple of log-log plots, so I am going to show 1 or 2 equations. I promise it's nothing too bad. Basically, the idea is what happens to a power law on a log-log plot is that it becomes linear. Okay, so I'm going to show you some log-log plots. If you see a straight line, that's a power law. And power laws are kind of significant whenever you see them in engineering or in terms of design, because they tend to be really catastrophic. So for example, when you have power laws describing the occurrence of avalanches or other events that release energy, power laws are catastrophic in the sense that the biggest events are responsible for most of the energy or damage that these things can have. And that's kind of because they don't have a characteristic scale. So many statistics that show up in sort of the natural world are what we call normal, if it's, you know, Gaussian, but, you know, maybe it's also exponential, things like this. These have characteristic scales, you know, avalanche, you know, you could imagine that avalanches might have a typical size and then a typical fluctuation size, but in fact, they seem to be power law in nature. And that's why they're so dangerous, because a single skier could trigger something really small or something really big. Okay, and why is it then that avalanches show power laws? Well, there's a really elegant theory that emerged in the 1980s. You can, you know, if you're looking for people related to this, Per Back from the Netherlands is one person. And you can illustrate self-organized criticality in a really simple experiment on the beach. So you can imagine taking some grains of sand and making a little sand pile. And what you'll see is that the sand pile will grow and grow and grow until you hit this critical slope. And at this critical slope, when you add grains of sand, you'll start seeing avalanches, where basically you add a single grain of sand and it can cause other grains of sand to fall and slide and create a little avalanche, a little sand avalanche. And it turns out that this phrase critical, this critical slope or this criticality, it actually has a connection to critical points in statistical physics or in thermodynamics. Critical points are when you have a phase transition. And at a phase transition, you see power law sized fluctuations or power law avalanches. And because you're at this phase transition where you have a difference in symmetries in the two phases, like say a liquid phase or solid phase, you have a high sensitivity to input. And this is called the susceptibility, and at a phase transition, it goes to infinity. So this is why a single skier, of course, can cause a gigantic avalanche that knocks out some Swiss village. Right, those are the essential features. Now, I want to kind of stress to you now that even though this is a winter talk, avalanches as a concept are everywhere. I'm just going to go through a quick few examples. So wildfires can be our avalanches and exhibit self-organized criticality. You have loading, trees grow, and then patches of forest are ignited by lightning or man-made causes, and then the whole forest burns down. And you actually see, power laws in the distribution of wildfire data. This is from China. And of course, earthquakes are a classic example. You see them on the Richter scale, and they are also power law distributed. And this is why they're so devastating. You can't plan for, earthquakes to all be a certain size because, you never know when the big one will hit. You see stock market fluctuations that also have this sort of power law shape. And of course, neuronal avalanches. If you look at neurons connected in either, say, a little petri dish or across the scale of the whole brain, you will see cascades of information or activation across the brain that are power law in scale. And this susceptibility point that I mentioned is actually sort of hypothesized to be, functionally useful. You want information to be able to propagate across the entire brain, but you don't want it to explode violently in sort of a supercritical sense. You can also see technological application of avalanches, photomultiplier tubes. In a photomultiplier tube, a photon comes in, knocks an electron free, and that electron knocks more electrons free because this whole thing has a voltage across it and creates an avalanche of electrons and then can be measured as a current. Of course, another place where avalanches appear in technology is in nuclear reactions. You have, instead of grains of sand or grains of snow, you have atomic nuclei that are split, emit neutrons that cause other nuclei to split. A critical reaction is what produces power. Supercritical is, of course, a bomb. Subcritical is a fizzle. Okay, that's enough about avalanches in general. Let's go back to snow, at least a little, briefly. What I want to highlight is that even though avalanches are ubiquitous collective phenomena, avalanches, particularly, snow avalanches, are complex. They have all sorts of rich dynamics, and they're highly sensitive to the local conditions. So just a simple thing here, what I'm showing you in the middle panels, these are pictures taken at different points in time of basically a bunch of beads, glass beads, on a felt slope. And this point here, that's just a needle, and it's used to knock a few beads loose, and they start, an avalanche. And with very small differences in the slope degree, you get quite different behavior. Here, in the lower angle, you see what will be like a slough avalanche in the mountains, where you sort of have this triangular cone. This is pretty safe if you're the one triggering it, because you're at the top of the avalanche, right? So, as long as nobody's down here, it's fine. Something over here on the right is a bit worse, though. Right now, the person triggering it's in the middle, and you actually see that the avalanche proceeds uphill from them, right? Because basically, as the snow below you gives way, it causes the snow above to also fall. And this is going to be more similar to slab avalanches, which can, catch. These are the most deadly type of avalanches, and this is what will catch skiers, in the middle of the avalanche. Okay, I'll also mention, of course, the slope and wind loading matter, things like if there's been rain recently to create an ice layer. But let's just finish up by looking at one more video of an avalanche. So this is one of my, of course, home skiing videos, taken conveniently with drone and helicopter. And what I want to highlight is this is an avalanche where the avalanche has actually traveled uphill of the skier. So as we zoom out, you should actually be able to see that the avalanche is actually proceeding far above where it was initially triggered. So we can see here, there's all this sort of liquid flowing flowing matter, but then actually the flow proceeds far uphill of where the initial triggering event happened, which is sort of on this cusp here. Okay, so that's it for my talk. If anyone has any questions, they can share them in the chat, and otherwise I'll let Raelyn proceed.
Thanks, Daniel. And again, please post things in the chat and we'll turn to Raelyn.
Hey. All right. Hello. So I'm Raelyn, and I'm going to be talking to you guys about ice spreading. So this is a project I did in conjunction with two other graduate students here at UBC, Adam Dong and Daniel Korchinski, who you just heard from. So let's set the stage. So there was this McGill Physics Hackathon. So what is a hackathon? So hackathon is a programming competition. And, 3 young physics students braved the hail and the tornadoes to complete this. So this was the weekend that Vancouver got some really, really weird weather. And I think a tornado actually touched down in the golf course. So that was kind of interesting. But the aim is to put together a project that involves scientific computation and the physical sciences in 24 hours. You only have 1 day to complete this. But, we're grad students. We're not as young as we were in undergrad, so it's really more like 12 hours. You got to do it in 12 hours. But everyone knows who's done a hackathon that the hardest thing to come up with is the idea. So what idea are you going to try and compute? So luckily, we'd come across this really cool paper about some experiments that were done on frost spreading and pattern formation on microstructured surfaces. So that's the title of the paper. And what they had done is they'd put supercooled water droplets onto a lattice. So supercooled water is super cool. So it's basically water that's below the freezing temperature, but hasn't actually yet gone through the phase transition from liquid to solid. And as you can kind of see in these GIFs, any small kind of disturbance causes this transition to occur. And this is actually something you could try in your own freezer at some point. So if you have some distilled water and you stick it in your freezer for kind of exactly the right amount of time, if you whack it on a table like this, it might all freeze. So yeah, it's pretty cool. But yeah, so they put these super cold water onto a lattice and they adjust the temperature and the humidity and watch as sites either evaporate or freeze, and then watch as the frozen sites kind of propagate outwards. And this was their experiment. Now, what we wanted to do was to replicate the experiment, but using simulations. This allows us to isolate the relevant physics, and then you get robust statistics. So you might only be able to do an experiment maybe 1 to 100 times, but you can do, computational experiments millions of times if you need to get the best, statistics. And yeah, real experiments are messy, so you can't control everything, and you never know if there's something small coming in and kind of ruining your results. And we wanted to design an algorithm that was, incorporating all the relevant physics, could run pretty quickly because again, we only had 12 hours kind of, and we wanted to be able to actually show the results that they had gotten, so show this frost spreading. Part of the reason this is kind of interesting is because frost spreading can affect things like airplanes, and the idea is like, what can you do to make a surface less likely to spread frost, because frost is kind of problematic, or maybe your windshields for those of you who live in commonly wintry areas. So here's the algorithm. So the idea is that there are 3 processes that can happen. So either you have spontaneous evaporation, which will happen at some rate we'll call lambda 1, spontaneous freezing, which will happen at rate lambda 2, and frost spreading by neighbors to other neighbors. So this happens quicker than liquid spontaneously becomes frozen. So a frozen site is more likely to freeze a site next to this. And we use something called a Gillespie algorithm. For those of you who've heard of it, it's a type of Monte Carlo simulation, and basically it's used in an effective way to simulate these different time processes. And it's actually often used by chemists to model chemical reactions. Yeah, so here is an example of, on the top 4 panels, is crystal growth. So we were simulating one single site in the middle freezing and then seeing how that frozen site propagated outwards. So light blue is ice, gray is still liquid sites, and black is evaporated sites. And you can see how it kind of mimics the actual experimental data they have, which is shown in the bottom 4 panels, so C to F. A to C is kind of interesting because it shows these like dendrite structures, these long tendrils that kind of come out. And depending on the humidity or the temperature that you have when you're going along, you'll get these different kind of blocky chunks of ice. So here you can kind of see how our experiment looked. And we don't really have those tendrils. So we didn't really get those long dendrite structures, which means we probably are missing some of the interesting physics. So it's something that we can kind of maybe work on a little bit more with our frost spreading model. And then the other thing we're looking at aside from crystal growth was just general ice spreading. So allowing multiple sites to start to freeze and then see how they kind of collectively spread outward. And of course, as you vary the different parameters, so those are lambda 1, 2, and 3 for us, but they kind of simulate or replicate humidity and temperature, will give you completely different kinds of structures at the end. So whether it's lots of small, tiny ice patches or large ice patches that almost cover the entire field of view. So an interesting thing about this is as you adjust the different rate parameters, so lambda 1 and lambda 3, or lambda 2 and lambda 3, for example, here, what you might expect is kind of a smooth transition from isolated crystals to singly connected crystals. What you actually see is this very sharp transition point. And for physicists, this is really exciting because it's an indication of a phase transition. So what it really means is that the system is really fundamentally changing from one system to the other. So for example, another phase transition you're familiar with is, liquid to ice or liquid to steam, for example. Those are kind of commonly known phase transitions. This is one that's typically known as percolation, and it's similar to the kinds of phase transitions that some of the ones that Daniel mentioned. So, neuronal avalanches, this might be an example of percolation, or, coffee is like a common one you've probably heard of. So water trickling through your coffee grounds is another one of these kinds of phase transitions. So yeah, so this is actually something that's really cool to statistical physics. I'm a cosmologist, so it's less exciting for me, but people got really excited. So yeah, the outcome of this project was that we actually won 2nd place in the hackathon. We did manage to reproduce the general phenomenology. We're definitely missing this dendrite structure, so maybe we need to add more physics. And we want to study this phase transition to understand it better. So this is something we actually are probably going to be pushing a little bit further, even beyond this project. So yeah, thank you for listening. All right.
Thanks, Raelyn. And again, questions for Raelyn, feel free to post in the chat, and we'll pass over to Simon.
Okay. So to continue on the topic of ice after Raelyn, I would like to talk about a few random winter facts about short track speed skating. This is a sport that I've practiced for many years up until I started university. And before I start, I want to make sure that everybody knows what a short track speed skating race looks like. So I'm going to show one of my old race here. And it's a race at the Canada Game in 2015. If you want to keep track, I'm in lane 1 over here. It's a 500 meter sprint. And it was actually in BC, in Prince George, that took place before. Perfect. And the first interesting thing I want to mention is that the first movement of skating is actually a running motion up until you have enough velocity to, at the first turn, start gliding. After that point, for the first turn and turn and a half, the skaters are gathering as much velocity as possible up until their maximum velocity. The most interesting point, both from a physics and from a technique point of view, is probably the apex, which is right here, the sharpest point in the curve. At that point, the radius of the curve is of about 8 meters, which is a very sharp turn. All the weight is on the right leg, and often the skater is going to have the left arm on the ice, acting as a pivot point without putting any weight on it. And this is a very difficult position to hold, and one that the equipment is kind of made to make a little easier. And I'm going to talk about this a little bit later. And I'm going to let this video play until the end because, of course, it wouldn't be short track speed skating without a little bit of goofing around, as the sport is known to be. So in the last turn, I lose equilibrium, but this allows us to show an example of a good finish, an interesting finish. So the motion for the finish is to raise the upper body a little bit to get some place, and then extend the left or right leg as much as possible with the blade flat on the ground. As you can see here, that my blade is flat on the ground and my opponent is up in the air, and this actually cost him the race by only a few thousandths of a second. Okay, so now that we've all seen a race of speed skating, let me take a step back and ask why we can skate at all. So why is ice slippery? Well, we commonly know that there's a film of water that lubricates the surface of the ice and allows one to skate. But physics have been very confused as to understand where this lubrication was coming from. There was the idea of pressure of the skater on the ice, an idea of friction, and another idea which is very important and I'm going to cover at the end. So first, let's talk about pressure. What we want to see is if the pressure of the skater could induce a change in the phase transition temperature from 0 degrees Celsius to minus 35 degrees Celsius, because it's possible to skate down to approximately this temperature. And what we can use to describe this is the Classilication relation, which describes the the slope of the coexistence curve. Here we are interested in ice and water, of course. So we're seeing a change in pressure and looking for a change in temperature. Here, L is the latent heat, the energy necessary for the transition. Delta V is the amount of melted ice to water. And then T is, of course, the temperature, which is 0 in this case. We can take approximate value for the weight of the skater, the area of the blade, and what we find is that this effect which was the accepted effect for a long time, is very minimal and would only change the transition temperature by less than 1 degree Celsius. So then we can ask, well, maybe it's only the friction of the blade on the ice that allows for skating. And this is a little harder to characterize. Here's an example for an atomic force microscopy tip, which I'm going to talk in a few seconds. And it's a little harder. In this case, they found that friction had very low impact, actually. But one broad example that we could give is that friction alone would probably not explain why ice is slippery, even if you are at rest. And the main contribution, actually, very interestingly, is that there is always a liquid layer on ice near the melting point, so minus 35 degrees and up. This is called a liquid-like layer and is a fully disordered layer of water, or water molecules on top of a rotationally disordered solid ice. And one can measure the thickness of this layer using atomic force microscopy measurements. This measurement uses piezoelectricity, which is an effect when you send a current through a material. Sometimes the certain material will change shape, which can be used to put a tip in quick oscillation, and then calculate the force between the tip and the surface of a sample to get topographic maps. Now this force will change whether it touches water or the ice, so we can calculate the thickness of the liquid-like layer, which was found to be 10 to 100 nanometer, depending on temperature, which is surprisingly thin, but apparently is enough to allow for skating to happen. And as well, in speed skating, we add water to the ice to make sure that there's always water before the race, and this makes the racing much easier. So we've covered how we are able to go forward while skating, but it's also interesting to consider the horizontal direction and talk about the lean angle. We can do a very quick calculation to calculate the lean angle as a function of velocity, and it's a very similar calculation that can be done with a bicycle or motorcycle. All we have to consider in the rest frame of the skater is the centrifugal force bringing the skater to the side, and the gravity bringing the skater downwards. And with this, we can compare the leaning angle to the velocity, and the only other relevant variables are the gravitational acceleration, of course, and the radius. The radius is assumed to be a circle, which is an approximation, but near the apex, we can assume that the turn is approximately a circle of radius 8 or 8.5. We can make sure that this makes sense, and in fact it does. So we can observe the pro skaters have maximum lean angle of about 25 degrees and maximum velocities of about 50 kilometers per hour. And also, if you are at zero velocity, of course, you don't have any lean angle. You are completely straight in the curve. This is a very difficult position to hold, so a lot of the equipment of the skater is made to help the skater be in this position and turn. There's a curvature, there's also a specific blade positioning, and of course, a specific way to make the blade, sharp. The most interesting is probably the curvature. First, we have a bend. So since the skaters always turn left, we have the blades that also turn left to help turning. This is called a banana in French, actually. However, if we have a bend in a blade that leans, we would only get 2 points of pressure, one in front and one at the back. To circumvent this, we have also a rocking angle in the other direction to have a continuous contact from the blade to the ice. And having a good bend and rocker is an art in speed skating that a lot of people spend their lifetime working on. But generally, the idea is that you're going to have a more intense curvature at the tip of the toe to be able to aggressively turn at the apex, and then a flatter curvature at the middle and the back of the blade to be able to go faster, since this reduces friction. Another thing you can see in this picture in particular is that the boots can go very close to the ice. You really don't want the boot to touch the ice, since this releases pressure from the blade and automatically results in a fall. So you can put the blades off center to pull the boot away from the blade, and also to give a feeling of grip to the skater. And this helps leaning forward without touching the ground. Lastly, I want to talk about sharpening of the blades, since it's quite different from hockey and figure skating. In figure skating, the blades are going to be hollow in the middle. This allows for very aggressive turns, which we don't really use in speed skating. So instead, we want a flat blade so that the friction is minimized. So for sharpening, for example, starting with damaged edge, we can use a roughing stone to have a rough sharpening, remove part of the top of the blade, which is going to bring deposits of metal on the sides. Those, at this point, of course, the blade is not sharp at all. You can chisel those away, removing most of them, bringing some of them up, and then polishing the rest to have as close as possible as a perfect rectangle. And it's really the edge of this rectangle being embedded in the ice which will allow to a good grip. Lastly, I want to end this presentation by saying that there are local speed skating clubs. There's one in Vancouver and one in Richmond. I'm not associated with them, but I'm sure they're great clubs, and I would encourage people with young children or adults as well, since there's adult group, to check the sport out. And with this, if you have any question, I'll be in the chat. Thank you.
Thanks, Simon. Ryan.
Yeah, let me pull up my video.
And again, please feel free to post. There's already some questions in the chat. Please feel free to post more.
So, as you have heard, I am Ryan, and I'm going to talk a little bit about the physics of snowboarding. And really, this is just an excuse for me to show clips from some recent videos that I think are really cool. So, for those who do not know what snowboarding is, it is this on the right. Basically, you're riding on a plank of wood with a sheet of fiberglass on top, and underneath what actually contacts the snow, what you're sliding on, is a sheet of polyethylene plastic, or PTEX. Right? There are some steel edges on the side, but those are really only used for turning, and I'm not going to be talking too much about turning today, so we can just kind of ignore those. Also, everything in this presentation, including this construction slide, does apply to skis as well. I'm just calling it the physics of snowboarding because, as you can see, I snowboard. So, Simone, already thank you, explained why ice is slippery. It's basically the same reasons why snowboards slide on snowflakes, right? Snowflakes are just little ice crystals. There is a tiny little semi or quasi-liquid layer on the top of any ice surface. That's always slippery. Additionally, there is some meltwater from friction and stuff, which can be used kind of to your advantage later, which I'll talk about in just a second. So, in snowboarding and in skiing, there are two main types of friction. The first is dry friction, and this is kind of the standard friction everybody thinks about, right? Two things just rubbing against each other. In this case, it's the polyethylene plastic base rubbing against ice crystals. Right? This is more dominant at lower temperatures when there's not really a lot of water in the snow. Right, on a really warm day, there's lots of water in the snow, which that water will help lubricate that friction or that sliding motion. And then additionally, there's also wet friction. This is basically due to the fact that water has surface tension. So on the right, on the bottom right, there's this nice little graph of actually the top little bar is a sheet of PTEX, the same material snowboards are made out of, and then a glass bead coated in water. And there's this little column of water attaching from the glass bead to the board, right? And it takes energy to stretch those, right? So this kind of actually sucks you down to the snow. And anybody that's skied late spring conditions, really warm up at Whistler in April or something, it probably knows that feeling where it feels like your snowboard is just kind of stuck to the snow. That's what's happening here. There are a couple ways to minimize the friction. The most common is just waxing. I am not a racer or cross-country skier or something. They know a lot about waxing. This is kind of the extent of my knowledge here, but basically, if it's really cold out, right, so you're really worried about dry friction, you just want to use wax that's harder than the snow, right? In that case, you'll break any sharp ice crystals and everything's fine. But say it's really warm out and there's a lot of water in the snow, you want to reduce that wet friction, right, that suction. So we want a wax that's hydrophobic. Polyfluorinated substances are really good at being hydrophobic, and so they've been in waxes at least probably since the 1960s. I don't know exactly, but they stick in the environment for a long time, and they're not really great for plants or animals or anything. So actually, there's a trend in the industry now to shift away from them, which is great. So the FIS, who is the governing body, behind snowboarding and skiing and stuff in the Olympics, has actually banned them starting this season. So that's great. And there are a lot more companies putting out eco-friendly waxes for high temperatures. So if you are a skier or snowboarder, do look into that. Additionally, another thing you can do is basically put tread on the bottom of your skis or your snowboard. And this sounds a little bit weird, but basically, if you imagine a rain tire, right, it's got all these channels in it to direct water away from the contact point. So if it's really wet out, you can put kind of coarse channels in the board. these are really small channels. You can just barely feel them with your fingertip, but they still do have the intended effect of just shuttling the water away from the board, right? And so if you reduce the total amount of water under your board on a wet day, you're going to reduce your wet friction and go a little bit faster. Additionally, on really cold days, you don't want that. You want to keep as much water under the board as possible because your limiting factor is that dry friction. So trying to put more water under your board or keep it around longer is better on cold days. So you can use a different type of base structure for that. Okay, so let's say it's middle of April. It's a really warm day. There's lots of water in the snow. You've got a nice eco-friendly warm weather wax. You've got a nice coarse base grind. So you can get a lot of speed on the snow, right? Well, what do you want to do? I think it's fun to jump off things, right? And so does this guy. Warning, he overshot this jump by about 50 feet, but he's fine. There's more clips later. So if I go and just take screenshots of this and then line them all up, what can we learn besides, maybe that he should have been wearing a helmet? If we just look at his trajectory, it looks like a parabola, right? This is just projectile motion. Now, snowboarders aren't exactly the spherical cow everybody learns about, in their first or second year of physics, but especially when they're grabbing and twisting and stuff, it's close enough. So to kind of illustrate this a little bit more, this is a clip of Jamie Anderson in her 2018 Olympic winning run, backside 540. Really cool. She won in 2014 as well, so she'll be competing again this year. So at the top here, this is an equation of motion basically for jumpers. And in general, it's a function of gravity and drag and lift. And that drag and lift does also depend on the speed of the wind, which is represented by the letter W here. Lift, for the most part, in situations like this can be ignored. I know that people do use lift for ski jumping and stuff, but they're really trying to take advantage of that to keep themselves in the air. In this case, if you're just tucking and spinning and stuff, it's mostly negligible. Drag is not quite as negligible, especially at this speed and over these distances, maybe 50 feet. But even if you just ignore all of that other stuff and just consider gravity and get the standard sort of parabola equation, it does follow the center of mass of the rider really well. And so that clip of Jamie Anderson, I lined up a bunch of shots and just plotted a parabola on top of it, and it follows her center of mass really well. So this is cool. And actually, we can use this information to kind of help us design safer jumps, right? So that one dude who just launched himself really far, how can we make that safer? There have actually been some papers written in the past 5 years on this, which is really cool that people are, have been putting research into this. The general theory behind everything in these papers is just that injuries occur due to the acceleration that the jumper experiences on landing, right? So to try to kind of minimize that, or at least have an idea, just kind of keep it constant, that's a good thing. So we can define an effective fall height, which is basically saying, if the jumper fell from half a meter just straight down, that's the same amount of force that they would experience on this jump. And in general, that's a function of the jumper's landing velocity, as well as the angles of the slope and the jumper's landing angle and all that stuff. It doesn't matter too much. But what's really cool is if we choose some value of an effective fall height. So say, I believe the US Terrain Park Council has said like 1.5 meters is like kind of the upper limit they want for, public terrain parks and stuff. You can design a jump, and the authors of these papers have actually implemented these nice little some things in web pages to design a jump that will give you, for any possible trajectory, the same effective fall height when that jumper lands, right? And so this little plot in the bottom here is basically just one of those jumps for some random parameters I've chosen, and it depends on the slope of the actual parent slope, and then how fast you're going, and the takeoff angle, and all this stuff. But it's really cool because you can just kind of design jumps now that aren't going to produce huge impacts. And so if you look at something like on the top right here, this is a standard kind of big air jump design this was actually, I believe, the one for the 2018 Olympics, and you'll see it again in this year's Olympics. If you come up just a little bit short, right? So there's this big landing slope. If you come up just a little bit short, you land on what's called the knuckle, this crease in between. That is quite a lot of impact and causes a lot of injury, right? And so this kind of effective fall height, the constant effective fall height thing, is just kind of eliminating that knuckle. And so the authors of those papers have went and created jumps like that. And so here is one of the ones that they were testing, I think one of the first ones they made actually on the bottom. It's, kind of flat and stuff, but you can still jump, maybe 20 feet. And in general, these are really good things to put in terrain parks, especially beginner terrain parks, right? People trying to learn how to jump, all that stuff. Obviously, professionals do want a lot of airtime and big height in between them and the landing and all that stuff. So this doesn't really apply quite as much to them. But I'm all about getting more people to snowboard and all that. So having, kind of more entry-level jumping that's not going to hurt as many people is really great. I think a lot of ski resorts are also interested in this as well, because it kind of helps them limit their liability, right, when people get injured in terrain parks. So I'll leave you with some other clips that I find cool from some recent snowboarding videos as I give you my final thoughts. Personally, the coolest thing about all of this to me is that once, these professionals have been doing it long enough that this trajectory, right, this projectile motion has just become intuitive to them. And so you can build these really big jumps in resorts or in the backcountry. So the next jump that's coming up is about 100 feet, right? And just based on, the way it looks, you can guess how much speed you need and do these really cool things over it, and it results in these really cool videos. So thank you for listening. And if you have any questions, you can put them in the chat. Thank you.
Thanks, Ryan. Lastly, Megan.
So to finish up this really awesome series of the physics of winter, I am going to be talking about the sport of curling. So while I appreciate that curling is quite popular in various regions of Canada, that may not be so universal internationally. So I'm going to start off by talking a little bit about the sport and how it's played and define some of my terminology that I'll be using. Curling originated in 16th century Scotland, and it has migrated about the world into places where Scottish people have emigrated to mostly. In Canada, it's quite popular. 6% of the Canadian population curls, and 22% of Canadians watch the sport, according to the statistics on Curling Canada. Additionally, Canada really does show up at the Olympics in this sport. It's been in the Olympics for 6 years, and Canadians have won 10 Olympic medals, 5 women, 5 men. Actually, we've medaled every single year except for in the most recent Olympics. It was quite the upset. So in terms of the actual game, there are 2 teams. They stand on the same side of this ice. This is a bird's eye view of what the ice looks like. And the point being is that you attempt to slide rocks from one end to the other with the intention of having your rock be on the button, is what that center ring is called. The scoring works that at the end of each team throwing each of their 8 rocks, whichever team has more rocks closest to the button relative to the other team will score that many points. So as you slide your rock, there are quite a few things that you have to take into consideration, being the weight, the rotation you put on it, what's going on at the other end. So this is really a team sport. One individual will throw a rock and then their teammates will sweep in an effort to sort of control the weight and the rotation. And then from there, it becomes quite the game of strategy. So one of the things you would typically think if you were on a blank sheet of ice and trying to get your rock to the center of the house, which is what the circles themselves are called, you would throw your rock and aim for the center. However, strategically speaking, this is not very good gameplay. Your opponent would throw their rock next and knock your rock right out of the house. Sequentially, you would just continue to do so until whoever was last scored 1 boring point. More typically, what happens at the beginning of one of these ends, they're called, where you're throwing your 8 rocks per team, is you set up what's called a guard. So you'll have several rocks at the top of the house or just past what's called the hog line. There's some interesting terminology in this sport. I don't know where all of it comes from, to be perfectly honest. So then once you have a guard set up, in order to actually score any points, what you have to do is you have to throw your rock so that it will actually curl around these guards. And so the interesting physics of this sport, there actually is a lot. I was very interested when I went to go look, just to look at the literature on curling. But the question that I'm going to be talking about a little bit more today is, how does this rock actually curl? And so I have a video to show you. I'm going to give you an example of what this looks like in real life, and just talking about actually how dramatic this lateral movement can be based off of just giving a very small amount of initial rotation on your rock when you throw it. So you can see she turns very slightly, and the rock is on the left of this center line. As it goes down the ice, it curls quite a bit, particularly at the end of its overall trajectory. So when you're throwing your rocks, you have to think of quite a few things. Her weight is really nice here, her curl, good. That would set up a fairly decent guard. However, once you get to the end of an end, you often have very many rocks in the house. You think about strategically trying to knock them out of the way, how you throw them, etc. So if you ask a curler, where does the curl come from? They have their own answer. They'll tell you that a large part of it is from the ice. So luckily, Simone has done some of the work for me today by talking about ice already. However, ice on a curling rink is dramatically different from if you're playing hockey, figure skating, speed skating, because they intentionally pebble the ice. So hopefully you can see in these images on the right that there is texture to this curling ice. And on the left, I am trying to show an individual who is actually going about making the pebbles by spraying water into the air, and it freezes before it can level out, giving it this textured surface. So in combination with that textured surface that your rock is traveling across, there is also something to consider, is the shape of your rock. So they look cylindrical, but they're actually not. On the bottom of them, they have this sort of ring shape or an annulus, where only a very small portion of the rock actually rests on the ice. So if you ask a curler, why does it curl? They'll answer, well, the ice is textured and you only have a little bit of the rock on the ice. So when you rotate it, it will curl in the direction you rotate. Well, for physicists, that's not a very satisfying explanation. First of all, it's quite interesting that it rotates in the direction that it curls. If you were to try that same thing with a water glass across a table, it would actually travel opposite to the direction in which it's rotating. If you try and rotate a hockey puck across ice, it will still have a straight linear trajectory. So those facts gave quite a good starting point to Shigalski and his curling friends and some of his colleagues when they were trying to answer this question of where does the curl come from. They determined that it is not curling by rotation alone. So Brian has very kindly done a lot of the legwork in describing what they initially thought was going on had to do with dry and wet friction. So you have this ring on the bottom of the rock exerting quite a bit of pressure per unit area, and that high pressure as the rock moves across the ice results in melting. So some of the rock they thought would be experiencing dry friction and some of the rock would be experiencing wet friction. And they had sort of this complicated explanation talking about how, well, as it rotates, there's several phases of different parts of the rock with the dry and the wet friction, and there's almost like a full page of equations in the paper to describe this motion. And then at the end of it, the conclusion was, well, this actually doesn't match our experiments that we have done very well. So this is somewhat of an explanation, but it's likely not the right one. And so over the course of study for like decades, Shigalski and his coworkers put out a first principles model that they called the pivot slide model. And they had much more success with this one to describe experimental results that they had observed. It very nicely explained that J trajectory that I had shown you earlier. And it nicely accounts for the relationship that they had observed between the lateral distance in which your rock moves and the number of rotations that the rock experiences as it goes down the ice. And this model is also consistent in observations that include sweeping, which I haven't really talked about much here, but it does have a large impact on both the linear distance and the lateral distance that your rock will travel. So this pivot slide model is, they say in the paper that it's very simple, but it's hard to describe in 20 words or less. Essentially, what's going on is that you have this texture of your ice, and as your rock slides down that texture, you have these sort of micro pivots as your rock is interacting with these pebbles. So in the paper, they kind of draw the analogy between a comb, and if you were to run your fingers across the comb, that you would, depending on how much pressure you exert, have the comb be deformed or experience some effect on your motion. So they break down the motion of the rock into a series of micro pivots and then sliding, and micro pivots and sliding as they interact with many, many, many pebbles across this textured ice surface. This does, like I said, does a lot better job of reproducing experimental results, so they were quite satisfied with this as an explanation. There are a lot of other details about curling that I did not have the opportunity to go into. There is expansive literature on the topic. And if you're interested, there are lots of televised curling events, and it doesn't actually take very much expertise to participate in curling. I know, because I'm not a very good curler. My whole family is much better. But yeah, I hope that you learned something about curling, or that it exists if you did not know previously. And thank you for listening.
Great. Thanks, Megan. And again, feel free to post questions in the chat. Let's thank all the speakers